Welcome to the Science program at the Niels Bohr International Academy 2016. You will now be able to watch a lecture given by Nima Arkani-Hamed, who is a professor at the Institute for Advanced Study in Princeton University. Nima Arkani-Hamed, or Nima as everybody calls him, is a fabulous figure in theoretical physics. He is bouncing with enthusiasm, he has deep insight, and he has worked on a variety of topics that range from, we can call it, classical phenomenology of particle physics to the deep structures that underlie quantum field theory. His lectures are famous. They're famous because he just radiates enthusiasm and a love of the subject. It is contagious. Students go away from lectures by Nima by feeling that this is the field, they chose the right field, this is what they want to work on. I'm sure you will enjoy the lecture.
Let me begin by reminding you that the dynamics of massless particles at low energies is largely fixed by Poincare invariance and unitarity. This is especially easy to think about in 4 dimensions, where if we think about massless particles, we can use these famous spinor helicity variables to parameterize the momentum for a massless particle in terms of these 2 bosonic spinors, lambda and lambda tilde. What's conceptually important about these variables is that the action of the little group, which is the real action of Lorentz transformations on an amplitude, which if you Lorentz transform the momenta, you have to pick up little group phases on the external states. It's these variables that the little group acts simply on, and in fact acts simply by rescaling lambda and lambda tilde by opposite amounts. And it's a very simple feature of the kinematics of momentum conservation for 3 particles that there's 2 ways that this can happen, with the lambdas all proportional to each other, or the lambda tildes all proportional to each other. The only invariants that we can build are contracting the lambdas and lambda tildes with epsilon symbols. And in this configuration, the only objects that we can have will depend on contracting the lambda tildes together with these square brackets. In this configuration, just contracting the lambdas with angle brackets. And the powers are entirely determined are entirely determined just by the helicities of the external particles. So up to the strength of the interaction, we know everything about what the 3 particle amplitudes are purely from Poincare invariance. We can move on from there to ask about real dynamics. So that's really almost purely kinematics. We can ask about dynamics now by asking for unitarity at weak coupling. And here the assumption of weak coupling is crucial because we're imagining that there's some limit of an underlying theory, or with some coupling becoming parametrically small, where the amplitudes have the simplest possible analytic structure, namely they only have poles. Well, the simplest possible analytic structure would be just polynomials, but then those are just contact interactions, so we're not seeing any particles being produced. If we have massless particles, we're not going to have that. We expect to have poles involving the massless particles. So, but that's the simplest possible analytic structure, is to have poles. And then there's a very concrete question, which is the only poles that we should have by locality are when either S or T or U at 4 points goes to 0. And on those poles, the amplitude has got to factorize into the product of 2 lower 3-point amplitudes. And since the 3-point amplitudes are completely nailed by our previous considerations, that's a very strong constraint on the 4-particle amplitude. For example, if you ask for interactions involving a single particle of spin S, just 1 particle of spin S, and you do it in this helicity configuration, minus S plus S plus S, then just trivially knowing what the 3-particle amplitudes are, you can just figure out what the residues look like. Okay, just the residue in the S channel. You see, up to these factors upstairs, which are have to be there just by having the correct helicity weights, there's an interesting feature that even the residue in the S channel has a pole in T, has something that looks like 1 over T when the spin is 1 and 1 over Tu when the spin is 2. But in any case, having figured out what those residues are, you can immediately write down the answer for the 4-particle amplitude, something that has that residue as S goes to 0 and then the analog in the other channels, and these things trivially work and we get the right answer. Okay? Now, there's something very basic about this, very basic and standard, but we see it particularly sharply and beautifully just by writing down the on-shell amplitudes that we see, which is that these 4-particle amplitudes already have a quite stringy character to them. What do I mean by that? Well, let's contrast the situation with the amplitude for a phi cubed theory, let's say, which I didn't write down, which would look like 1 over S plus 1 over T plus 1 over U. Okay? So that splits up into the sum over an S and a T and a U channel. Okay? And so you can physically think about those three different processes taking place. In other words, the unitarity, the fact that the answer comes as a sum over channels, is completely manifest. That is not true when we're talking about gravity or Yang-Mills theory. This factor is forced to be there just by weight considerations, and there's a product of ST and U downstairs. This cannot be written as a sum over different channels, preserving Lorentz invariance. Okay, and that's just seeing the avatar of the very famous fact that we all know of the tension between locality and unitarity when we have massless particles with spin. Here we just see it in the amplitude itself, that it just simply cannot be split into the sum over different channels. If we go to the maximally supersymmetric version of this, there's a delta 16 of Q upstairs. And there too, it's impossible to express this as a sum over ST and U channels. And that's the one-line explanation for why there's no such thing as off-shell superspace with maximal supersymmetry. If there was, the Feynman diagrams of that ersatz theory would, every single one would give you a delta 16 of Q because of the supersymmetry, and you would be able to split it up into a sum of ST and U channels. That is impossible. Okay, so already, even the massless particle scattering has this feature that we are normally used to seeing in string theory, that we can't split things into different channels independently. Okay, so much for the story of the theories that we know and love. What about higher spins? Well, massless higher spins are actually ruled out by the existence of ordinary gravity. And they're ruled out by attempting to write down consistent 4-particle amplitudes for processes like this involving a massless higher spin particle or 2 massless higher spin particles even more canonically. And it's a very simple exercise to just work out the analog of what we did in the previous slide, what the residue can look like in the S channel. And now you discover that it has to have even a higher order poles downstairs, not just the 1 over TU, but it has to have even higher order poles. And that makes it impossible to be consistent with a 4-particle amplitude that only has poles in S, T, or U. So that's the one-line explanation for why the existence of ordinary gravity, or if we have charged particles, charged under E and M or under ordinary Yang-Mills interactions, they're also impossible by the same reason. And so one can follow this logic to its end, classify all the possible theories that you can have of massless particles with spin, and discover that the only consistent theories are the ones that we know and love, and all the massless higher spin things are ruled out. This is assuming that we have a theory with a finite number of massless higher spins, and I suspect even the finite number does not matter there. Okay, so it's the masslessness, and we're in flat space. We're not in ADS. We're in flat space. We're asking for interacting theories. M Planck is not infinity. So just having gravity, ordinary gravity, makes the existence of massless higher spins impossible. Yeah.
What principle, physical principle?
Unitarity. It's unitarity which is ruling out. They're not. No, those guys are fine. Those guys are fine, and yeah, including those, of course. Yeah, no, but I said at low enough energies. Okay, so we can of course include those as well, but we also discover just by following this. These are fairly standard arguments. We discover that the ones that are most important at low energies are the ones that we know and love. Of course, we can have, for example, we can have all plus or all minus amplitudes, and they correspond to trace F cubed or trace R cubed couplings. Okay, so but we can also see just from the usual dimensional analysis, also just from here, that they correspond to. Sorry? That's right. Exactly. So that's why I said here. Yes, this is why what I said here is it's the existence of ordinary gravity that makes, with the usual plus minus interaction, that rules out the presence of higher spin particles. It is entirely possible, of course it's entirely consistent to have theories that only have these dumb couplings, like R cubed, F cubed, linearized R cubed and F cubed and higher spin, and they're all okay, but it's the existence of ordinary gravity, things that makes, planets go around in orbits and stuff like that. It's that makes higher spin particles impossible. All right, so then there's a very concrete, very obvious question, which is, so the dynamics is isn't almost entirely fixed at low energies by Poincare invariance and unitarity. The only problem is that the amplitudes get large for gravity as we go to high energies. It's not just in gravity, it's gravity in 4 dimensions. But we can ask a slightly more general question. It's the amplitudes get large in Yang-Mills in 5 dimensions, and for phi cube theory, they get large in 7 dimensions. There's a high enough dimension where all these things break down. Okay? So we can ask a slightly more general question. Is it possible to UV improve the theory you have to change something, so obviously you have to add additional particles. We're going to continue to imagine that things are weakly coupled. And so we can ask, can we UV improve the high energy theory relative to the low energy one just by adding some number of massive particles? Okay, so we're very used to that with the story of the electroweak pions, the longitudinal components of the W and the Z in the standard model, where if we look at the low energy amplitude, it starts off life as minus S plus T. And now we can ask, how do I fix this up as I go to very high energies? Very high energy fixed angle scattering. I want to make demand that the amplitudes don't get bigger than some fixed small number. And I can do that just by sticking in front of this S a 1 over 1 minus m squared. And in front of the T, the analogous factor. So I can take this guy and replace it by that. And now this is, of course, totally fine at high energies, and it's exactly what we get if there's an underlying Higgs model. So, in fact, going back a step, that's also how we discovered W's to begin with, right? So we are UV completing the 4 Fermi interaction in this way. Then the longitudinal components of the W and Z's asked us to introduce Higgses in this way. And of course, once you see that you have the Higgses, you have to check that the Higgs scatterings are okay as well. But here we know that, of course, we can do it. So now we can ask the analogous question for gravity or Yang-Mills or any theory, really. Is it possible to UV improve the high energy behavior of the theory relative to the low energy one? And the rules are, of course, A, that it has to reduce to the right answer at low energies. B, it has to be smaller than a fixed constant at worst at high energies fixed angle. And then there's a few other rules. C, obviously, we only want to have poles when S, T, and U are positive. We don't want to have tachyons. Now, there's a very familiar ancient requirement from causality that tells you that for fixed negative T, which would correspond to particles scattering at very large distances relative to each other, for fixed negative T, the amplitude should be bounded by a particular polynomial. It should be bounded by S squared. That's a very basic consequence of causality. This rules out really dumb ways you could UV complete things if you weren't thinking about causality. Like you could take any amplitude and multiply it by e to the negative S squared plus T squared plus U squared. Totally idiot thing, which would obviously fix it at very high energies. And you could do a million things like that. But they're all ruled out by running afoul of this basic requirement. These things are relatively easy. What will be the most constraining thing that we'll talk about is unitarity, which really tells us that on one of these poles we have to be able to consistently interpret what we see as the production of some higher spin particle. And very often unitarity turns into a positivity condition if the particles 1 and 2 on the left and 3 and 4 on the right happen to be the same. Then we get squares of coupling constants here, so the residue has even got to be, has to have a positivity condition, but really what's really important is the unitarity condition. And ultimately, of course, just like in this case, we need consistency for all states, massless and massive. Yes?
The proof of the S squared, which is a 4-dimensional thing, even though it's an arbitrary dimension, requires...
No, it's not a 4-dimensional thing. It does hold in string theory, of course. No, but we don't want polynomial boundedness, only for fixed negative T. Yeah. Well, we can talk about that. I mean, there's a whole discussion. There's a whole discussion to be had about why we want this bound. It's not just analyticity, no, but it is causality. It's the relativistic analog of the fact that when we prove that the index of refraction has got to be greater than 1, that well, but essentially, I mean, qualitatively, almost quantitatively, the point is that you have to be able to throw out contributions at infinity. Right.
But there are, it doesn't have to be polynomially bounded to get those.
It's not polynomially bounded everywhere, but it is polynomially bounded at large S for fixed t, for fixed negative t. Right. That's right. But for those proofs, and there's various ways of talking about it. There are ways of relating it to there's ways of relating it directly to superluminal propagation in interesting backgrounds. They all involve going to in fact, really strictly, we want it to be for t equals negative epsilon. For arbitrarily small negative t, you have to be bound, but then you really are bounded by s squared, and the power is 2 in any number of dimensions. And it's of course it's satisfied in string theory. It's but yeah, we can have more of a discussion about exactly what this. I agree, it's not a 100% theorem, but well, we're going to use it as a working assumption. Certainly, stupid things like e to the minus s squared plus t squared, those are obviously totally screwed by a causality, simply because you can't shove in form factors in Euclidean space and expect, when you analytically continue to Minkowski space, for anything good to happen. You get things that give you both time advance and retarded effects. Okay, so that's why it's very important to have polynomial boundedness. Why the particular power is 2 and so on needs a little bit more of an argument, but I'm going to assume it. Okay, so the first point to make is what is it that makes the problem challenging? So we have these easy to UV complete theories like the nonlinear sigma model, but we have these hard to UV complete theories like gravity or Yang-Mills theory in high enough dimensions, or even phi cube theory for that matter in high enough dimensions. So what is it that makes the hard theories hard? The answer is that what makes them hard is the existence of a 3-point interaction, which means that we have massless STU channel poles already in the 4-particle amplitudes, already at low energies. Now, there's a very quick argument that shows that when this is true, it's actually impossible to UV improve with a finite number of massive particles. You have to have an infinite number of particles and an infinite tower of spins in order to simply UV improve the high energy amplitude relative to the low energy one. And instead of boringly going through the proof, let me just give you a trivial example, just to show you it has nothing to do with gravity or anything. It really has to do with long range forces, or really more precisely the existence of that 3-point vertex. If we have a phi cube theory, here's the amplitude, and let's say my goal in life is to make the high energy amplitude die even faster than this 1 over s that it appears to already at tree level here. Well, let me try to do the same game I did with the Higgs, add these extra poles downstairs to make it go down even faster. And now you see that unlike the case of the Higgs, it's impossible because the residue on this pole is guaranteed to be negative. Okay? So I can do it, but only if there are ghosts. And ultimately, it has to do with the fact that unlike the Higgs case, where we had no a priori expectation for the sign of the low energy amplitude, it has to be negative s plus t in order for it to be UV completable. Okay? Here, we do know ahead of time the signs of the low energy residues, and once they're fixed, it's forced, the UV completion forces, if we have a finite number of particles, forces there to be some minus signs for the rest of the spectrum. So the UV completion needs an infinite number of particles and infinite tower of spins. Yes. Exactly. Yes, exactly. No, I mean, no, it's not. It's not so much even the masslessness. Of course, for massless spin 1 and massless spin 2, they're forced to be massless. Of course, it doesn't actually matter for a phi cube case if it's literally massless, but it's something light. It's something light. Yeah. Definitely, yes. It definitely matters that it's not of order. That it's not of order the scale where the new particles come in. Certainly, yeah. Yeah, if all these guys were comparable to each other, you're right. But I'm saying, to the extent that there's a hierarchy between the mass of the particle that you're talking about and the mass where the new things come in, then you cannot do it. Yeah.
But in theory, where I am at, if I start modifying, adding what,
Anyway, David, yeah.
is that we have a UV issue that's higher than the operators enter. It doesn't affect the masses of heating water.
Sure. That may or may not change the story for phi cube theory. It's not going to change the theory for gravity or Yang mills, where they're forced to be massless. They are just massless from degrees of freedom considerations. Phi to the 4 is phi to the 4 is phi to the 4 all by itself is okay, and yeah. No, what I'm trying to do, phi 4 goes in the wrong direction. Okay, what I'm trying to do is what I'm trying to do is make the high energy amplitude even softer at high energies than what you would naively get at low energies. I'm just trying to improve the power. Phi to the 4 goes in the wrong direction. It's harder. Okay, so what I'm trying, that's why we're not used to any UV completions of phi cube theory. Never mind the fact that it's never mind the fact that there's a non-perturbative instability. Okay, but we can get phi cubed interactions in string theory, right? We can get effective theories of phi cube theories in the bosonic string compactified on a circle with self-dual radius. Say, okay, so in theory, we don't know of any theories that UV complete. In the sense of making the high energy behavior better than the low energy one, other than something stringy. And I'm trying to explain why. There's a very qualitative fact that when you have long range forces, when you have long range interactions, it's impossible to do it with a finite number of particles. Okay? You have to have an infinite number of particles and an infinite tower of spins. Okay, so this then defines
there is the other out that you have to admit, which is that you have degenerate spectra of these extra particles, all of which accumulate at the same point. Since you're doing everything perturbatively, you can't avoid that.
Yeah, so we'll even give an example of I mean, of course, we'll talk a little bit about accumulation points in a moment. But yes, I mean, what I'm assuming here is that at any m squared, there's a finite number of new particles that are coming in. Okay, and yeah, and so it's not like something like the hydrogen atom, where there is where there's an accumulation of bound states and then a continuum above it. Right.
Since you're trying to rederive string theory, you're assuming everything that works in string theory and things that.
Well, I'm going to have a hard enough time doing it, even assuming everything I know about string theory. So I'm very happy to do that. And so, yeah. Well, that's the goal. So, all right. But I think. Well, okay. Let's. This is actually what I'm just coming to. So anyway, there's a very well-defined UV completion S matrix program just at 4 points to imagining we have gravitons and gluons on the outside, find some high energy amplitude that satisfies the rules, as well as all the extra massive particles that are going to have to come in for a ride, which are going to have to include particles of arbitrary high masses and spins. Okay, so this is the UV completion S matrix program, and we can ask what's new compared to the 60s. Then, well, I wasn't around, but most of the literature was obsessed with amplitudes for massive scalars. And that's perfectly fine. There was a hope that the consistency conditions, analyticity, locality, unitarity, etc., would fix the answer to be unique. Now, of course, we know that there are two things that were wrong with this idea. One of them is that we know that the answer couldn't possibly be unique. There's a continuous infinity of possible theories. Any large N Yang-Mills theory will satisfy all these rules, so there's no way the answer would be unique. But putting that aside, also, we didn't actually a priori know what the rules for incorporating locality and unitarity really were. That's why a lot of you open up the analytic S matrix book, they compute a lot of Feynman diagrams. They cheat in order to see what the rules are, and they go back to try to pretend they didn't know them and impose the rules. But we actually didn't have an a priori understanding of what those rules were. And that's important if you don't have a weak coupling. You don't have this organization of the amplitude into pieces, rational, dilogues, four logs, and more complicated. Now we're talking about weakly coupled theories where we know what the rules are exactly. I'll be more explicit about them in a moment. So we don't have the second problem. What about the first problem, that there's a continuous infinity of such theories? Well, now the focus is instead going to be on massless gravitons and gluons. And here I think it's important to remember that, at least for the case of gravity, perturbative string theory, the perturbative string theories are the only known answers we have to this problem. Okay? After everything else that we've learned, for the question of even just the S matrix in flat space, there aren't a continuous infinity of known answers already. We only know perturbative string theories. And another reason why this is why dealing with gravity is going to be significant is, remember, we're going to have to be dealing with an infinite tower of higher and higher spin particles. Recall that at least when the particles were massless, it was the interaction with gravity that rules out their existence. So since we're now talking about trying to UV complete gravity, it's clear that we're going to get much, much stronger constraints, because it's the very thing that makes the presence of these higher spin states apparently impossible in the massless limit. Yes?
So as far as I understand, you're not just looking for a UV completion,
A weakly coupled UV completion. Yes, yes. Yes, it's absolutely weakly coupled. Absolutely weakly coupled. No. We're just asking this limited question. It's an interesting fact about the real world that it appears weakly coupled, certainly at energies that we've probed, and if we extrapolate, it looks weakly coupled all the way up to the gut scale. Nothing is breaking down. So we don't have indication for extra strong stuff in the real world, but of course, one could easily imagine all sorts of other things. I'm just asking this limited question. I'm just pursuing, we discovered the W and the Higgs, and what would you do if you're trying to do to gravity what we did with the weak interactions and with WW scattering? That's all, okay? Just the... My motivation is my motivation is A, theoretical, because it's the easiest question of this sort that I could ask, and B, a little bit experimental, that it sure seems that like nature is weakly coupled all the way up to the gut scale, or the string scale, or the Planck scale. Okay, so there is something. Nature has been kind to us, despite all of our obsession with solving strongly coupled theories. Even strongly coupled conformal theories, we don't seem to see any in our relativistic vacuum anyway. Okay. Now, just a trivial comment. I'm going to be focusing on 4-point scattering. Obviously, we have to have endpoint amplitudes. We can't just have 4-point scattering. We have to have consistent endpoint amplitudes and consistent factorization at endpoints. Okay, not just 3 on one side and 3 on the other, but these amplitudes have to factorize correctly in all possible channels. A proxy for this is looking at consistency of 4-point scattering involving the massive higher spin states. So if you imagine you had a 5-point amplitude, then saying that it factors consistently, you would have to know that it factors consistently in the intermediate channels. You could have the massive guys propagate. So the consistent factorization is definitely having the 4 points factorized properly is including the massive states is a critical ingredient for the higher factorization as well. Okay, now, before trying to prove anything, we're not going to prove very much, but it's amusing to just go back to the amplitudes and make the dumbest possible guess for what a UV completion is, because the dumbest possible guess lands you on the right answer that we get in string theory. Recall this interesting fact that I stressed, that when it's a product of ST and U, that the gravity amplitude has this product structure in ST and U, okay, that you can't split it into separate poles. If we just imagine that that continues to be the case in whatever the UV completed amplitude is, so if we imagine the UV completed amplitude also has this product structure, then in a few lines we get to this answer, okay? And let me just give you the brief structure of the argument. Whatever the answer is, if it's this product structure, we have some products, we have some poles in ST and U, which I've written as negative S, negative T, and some roots in S, T, and U. So we have a product over over poles and a product over roots. And now you see how non-trivial it is, okay? Because at a pole at some s equals some particular r star, you're in danger of having double poles in T. Okay? And that's a complete disaster. Later we're going to talk about much more nuanced things about positive polynomials and Gegenbauer expansions and so on. But they have to at least be polynomials. Okay? They're not even polynomials. Okay? They'll have t's downstairs. So that means that these roots upstairs have to kill the double poles that you get downstairs. And just doing that immediately tells you that the set of all these zeros upstairs, negative zeros upstairs, has got to coincide with the set, or has got to contain the set of all possible sums of roots downstairs. Okay? You can check that very easily from, let's say, s goes to some particular r star. The fact that we get the sums of roots is that here in this T we get a sum of the two roots appearing there. Next, if we demand the correct massless residue here, as s goes to 0, we should get a 1 over tu, which is really negative 1 over t squared. That further tells you that this set of roots, the set of the roots has got to be the same as the set of the sum of the roots. And that tells you what that set has got to look like. There's got to be a smallest such pole, and the rest of them have just got to be m squared times an integer spectrum. Okay? Yeah. Oh, well, I'm just assuming that I can give it a. None of this is a rigorous, so I'm just assuming that f of s is characterized by its zeros and its poles. You know, it's partially, yeah. Yes. It's going to the factorized form, and then just a little bit more, just a tiny bit more from the causality restriction of polynomial boundedness at fixed t than that. Yeah. Yes, absolutely. I'm not. That's why I say it's a simplest guess, but I'm saying that it's a guess which is very strongly motivated by this interesting structure that we already got for the massless case. I'm just saying if we make that guess, then we immediately get this structure, which is just the Virasoro-Shapiro amplitude. So that matches the string amplitude. Now, actually, what do I mean by the string amplitude? Because there's a number of perturbative string theories. Well, first there's a trivial point that the 4-point tree amplitude is completely independent of however you do the compactification. Okay, so you can compactify any way you want, but as far as this amplitude is concerned, it's totally independent of it. But there's something else which is kind of amusing. It wasn't at least obvious to me ahead of time. But if we look at the gravity amplitudes, let's say, in type 2, the heterotic string and the bosonic string, they all look like the following. They all have this basic factor, but they really split up into pieces that are associated with the low energy 3-particle amplitudes. So for example, in type 2, we just have the minus 1 over STU factor, which is associated with the fact that we have this basic gravity amplitude that's got to be there in any gravitational theory. And the heterotic string, there's this new piece, this 1 over S1 plus S, that you can think of as being associated with a new vertex, which is there in the heterotic string, which is not there in the type 2 string, between 2 gravitons and a dilaton. Okay? So this is a little bit non-trivial, that the final answer breaks up into pieces that are gamma-dressed of what you get associated with the low-energy 3-particle amplitudes that you have in the theory. And even in the bosonic string, there are 3 pieces that come from this guy, that guy, as well as a coupling of the 2 gravitons to the tachyon. Anyway, the same thing is true, the analogous thing is true in Yang-Mills theory. And so these 2 structures are really universal. They're always there, and they're associated with the most primitive universal 3-point gravity and Yang-Mills amplitudes that we have. Okay. So what we'd like to see is, well, how much of all of this structure is forced on us just by trying to UV complete gravity. Okay, that's the first most naive question, the question of the title of the talk. But obviously, the real goal of this exercise isn't the academic exercise of deriving perturbative strings. I actually couldn't, and you know, as we even see from some of the previous discussion, anytime you try to derive something, you often put in many assumptions, and there could be loopholes and so on. I'm always very skeptical of derivations. What's important is new formulas that give you new insights into things that you didn't have before. Yeah. I don't know. I don't know. That would be a very nice thing to of course, we know how to do it other ways, but from this point of view, right. Definitely not. Definitely not. Yes, yes. I entirely agree. I entirely agree. That's why I said checking factorization, not just for the massless guys, but for the massive ones, is the first proxy for going to a 5 points and higher points. But of course, what you want is an endpoint generalization and a consistently factorizing endpoint generalization. But let me. Yeah. No. No, because contact terms I don't want to have. Contact terms, no, because it's my rules. My rules is I want to UV improve the amplitude. So contact term always messes it up. Contact term always makes the amplitude gets even worse at high energies compared to low. What I'm trying to do is improve the high energy behavior of the theory relative to the low energy one. So I cannot do dumb things like add contact terms. Okay, we'll see similar things that we can do, anyway, this is at least my own goal, is to try to understand perturbative strings in a new way where the worldsheet picture is not primary. And the moving analogy in my mind is the story that's been developing in the context of gauge theories. Okay? So there we have a time-honored, fantastic, standard way of thinking about gauge theories using Lagrangians in a gauge-redundant way, and that's perfectly great. But over the last 10, 15 years, we've started to develop a second point of view about gauge theories and gravity, which is you start with the basic 3-particle amplitudes. Now, at this level, you can already check that the 4-particle amplitudes are consistent. Great, okay? So that's part 0 of the story. But then you don't slavishly keep going and say, now I'll write down an ansatz for the 5-point and check it, the 6-point and you check it, right? Now you start discovering new things you can do with these objects that you didn't think of doing 20 or 30 or 40 years ago. These are things that we started thinking of doing 10 years ago, 5 years ago, which is to start gluing them together on shell to build on-shell pictures like this. And these turn out to give you very, very different representations of the amplitude. And while they're derived from field theory, they start gradually getting further and further away from the conventional picture of the underlying field theory. They start bringing out some of the symmetries that are totally invisible in the Lagrangian. For example, these pictures and their association with the positive Grassmannian makes the Yangian manifest, which is just a little baby part of the U-duality of the dual string theory, just the fermionic T-duality. But still, you want to make fermionic T-duality manifest. You're not going to see it here. You're going to see it once you start gluing these basic objects, not slavishly checking whether the theory works, but gluing them together and discovering more interesting representations of amplitudes that you could build from them. And this process goes on for a while until there's a break and you discover some autonomous object with a life of its own on the other side, which is the mother of all these things. That's the story with the amplitahedron and something called the dual amplitahedron that none of you are going to Berlin tomorrow, but you will hear about if you're in Berlin tomorrow. Okay? Anyway, so that's the basic analogy in my mind, that the usual gauge redundant picture, it's an analogy, it's not exactly the same. But 20 years ago, it might have seemed insane. 30 years ago, it might have seemed insane. There's any other better way of thinking about Yang-Mills amplitudes other than starting from the Lagrangian. Just like today, it could seem insane that there is no better way of thinking about perturbative string amplitudes other than starting with the worldsheet. But by looking at the invariant content, the actual answers, we can start seeing how to organize them in different ways and bring out different structures. At any rate, this may or may not go anywhere, but I think it is the obvious next step in the amplitudes program.
When one was at a model started with 3 amplitudes for on-shell particles.
But none of this was done. You see, none of this was done. None of that was done 30 years ago. Well, none of this, these pictures are not drawn 30 years ago. These pictures are not drawn 30 years ago. The ways of, I think you could say that they could have been.
They were. That's how the loop amplitudes were first constructed, by gluing together on-shell 3 amplitudes particles.
To some extent, using the Feynman tree theorem to some extent, and right, but it was not understood perfectly, and well.
What was discovered indeed was whatever you're looking for, which is the 2-dimensional CFT sum over surface. But it was discovered by exactly unitarity in a totally on-shell formula.
Well, I think that I mean, there's a philosophical point, but there's a technical point, and I think we can talk about the philosophy a lot more. The technical point is that in none of these developments in Yang-Mills theories does the word polarization vector make any appearance. Okay, we have a completely non-gauge redundant way of talking about the objects, and very importantly, these pieces do not have any usual space-time interpretation. String amplitudes, the pieces most certainly have a space-time interpretation. Of course, it's not completely obvious right away, but they're thickened Feynman diagrams. And polarization vectors are the stars of the show. They're there. You need polarization vectors all over the place. What I'm after is some non-gauge redundant way of talking about perturbative string amplitudes, which has some of this flavor to it. Okay? And that's the technical point. I don't want to see polarization vectors. Right? Yeah. Right.
Putting together two scalars going to infinite number, any number of particles with arbitrary scales. That
Right.
is what is required for the new
Right.
things together. So those polarization vectors and on-shell were all described by then, having derived a complete set of tree diagrams for all the particles.
Right. Except when we right, but I understand there are no off-shell rules, but now we're talking about massless gluons and gravitons, and even their description, even in standard perturbative string theory, involves these polarization vectors, involves this gauge redundancy, and we love the gauge redundancy so much in perturbative string theory we extend it to be sigma dependent on the world sheet. I'm after something where the gauge redundancy does not make an appearance, and which will force the basic objects to not be as closely tied to space-time scattering processes as they are with Feynman diagrams, equally well with perturbative strings. Maybe it doesn't exist, but as I said, at least to my mind, it seems odd for there to exist some totally differently redundant, if not gauge redundant, but involving very different objects' ways of talking about ordinary Yang-Mills theory, given that perturbative string theory's attitude towards gauge redundancy is that more is better, it seems strange for there not to exist. There are polarization vectors, and the usual gauge transformations are even elevated to infinitely more gauge transformations to eliminate all the bad modes of the higher spin fields, which have sigma dependence on the world sheet. Okay? So associated with the fact that we have this very gauge redundant way of talking about perturbative string amplitudes is our very poor state of knowledge for what the covariant content of the theory is, for what the actual on-shell amplitudes are, apart from formally being able to write them down, actually knowing what they are. And I think this is not a technicality, but is an indication of some, potentially, is an indication of a different way of thinking about things. But that's a hope. All we're doing here is taking some very baby steps just to clear the brushes and see whether anything like this might exist. Now, I have, wow, I'm completely fucked. So, okay, so let's see what I can do in my remaining 15 minutes. 15 minutes, all right. So, I will not rifle through all these slides, but I'll give you some highlights, okay? So, first I want to mention part one, what the rules for this 4-point S matrix program are very concretely for any masses and spins. This really just involves an extension of the spinor helicity formalism understanding of 3 particle amplitudes to any mass and spin, which is straightforward. I wasn't aware of it in the literature, but it's something quite easy and straightforward. Then we'll take a first look at stringy magic with only massless external states. And we'll play with some deformations. So we'll see how non-trivial it is that string theory, even just with a massless external state, satisfies the rules. And then we'll see that it's possible to deform just 4 particle amplitudes just with the massless states, borrowing some of this magic. That just highlights the fact that we need to do more than just talk about the massless external states. The higher spin states matters too. I'll probably have 0 time to talk about this, which is a picture for where some of these, there are some really miraculous facts about unitarity that show up in part 2, And part 3 is not directly related to part 2, but may be related to it. This is some work in progress with my student, Laurencio Rodina and Jaroslav Trinka, that's motivated by the general problem of reconstructing local bulk space-time physics just given the S matrix, just given the data of the S matrix. How do you know that you can produce it from underlying Feynman diagrams? And we'll see that there's a very algebraic structure that controls it. That algebraic structure makes unitarity a derived quantity from gauge redundancy. It's kind of backwards from some of the usual ways we think about amplitudes. But its algebraic nature makes me, is at least hints that something like that might extend for the string S matrix problem. And then I'll end with some open problems and outlook. All right, so let's go rapidly through some of these points. So first, the rules for 4-particle S matrices, and really what I want to know is how should I characterize this 4-particle amplitude, and what is the factorization check that I need to do? All right, now if we just had external scalars, this is very easy in any number of dimensions. And if I have 2 scalars, 1 and 2, and they couple to a particle of spin s, we can just write down the on-shell amplitude trivially. I just have a symmetric transverse traceless polarization vector for this guy. And the only thing I can do is dot it into P1 minus P2. Everything else gives me 0. So this is what the 3-particle amplitude looks like. So I know what the 3-particle amplitude is, and if I have 4 particles, the residue in the S channel has got to factor into the product of the 2 couplings, and I just have to sum over these. I have to sum over the polarizations of this symmetric traceless transverse tensor on one side and the other. And doing that, and in particular making sure that it's traceless, taking out all the traces, gives me in the end, when I dot into P1 minus P2 on this side and P3 minus P4 on the other side, the Gegenbauer polynomials. So what I have to get, if I'm in d spatial dimensions, with a particle of spin s being exchanged, the residue has got to be the s, the Gegenbauer polynomial of cos theta, which of course I can translate into t in the standard way, relating t in the scattering angle. Now the Gegenbauer polynomials are just the orthogonal polynomials on a sphere in any number of dimensions. Here is a simple generating function for all of them. And the important point, we'll just write down the first few. For a scalar is 1. For spin 1, it's just cosine theta. For spin 2 is the first time the dimensionality of space matters. It's d cos squared theta minus 1, and so on. All right. What's the difficulty? What's the difficulty of generalizing this to any spin? Well, it's just, I don't think there's any fundamental difficulty. I haven't seen it done anywhere. But you have to take care of all those things. You have to write down all the possible tensor structure. If it's not just scalars on the outside, it's harder. And the polarization sums are more of a pain in the butt. Okay? However, life is very easy in 3+1 dimensions, which happens to be where we live, which is also good. And that's because in 3+1 dimensions, both the massless and the massive little groups are as simple as possible. The massless little group we just talked about is just this rescaling of the spinor helicity variables, but the massive little group is also totally trivial. It's just SU2. Okay, it's the easiest, it's the simplest non-abelian group. And so we can use that fact to our advantage. For example, the usual way you would talk about a massive spin 1 particle is with a polarization vector, a transverse polarization vector, right? That means that it's something that has an alpha and an alpha dot index. But there's an easier way to think about what it is, which is that you can always use the momentum of the particle as an intertwiner that can switch alpha indices to alpha dot indices. And nothing stops you from just, for example, using all dotted indices or all undotted indices. And if we do that, then the polarization vector is even easier. These alpha beta indices turn into the little group indices literally when you restrict to the little group. And so what should they be? They should be representations of SU2. What are representations of SU2? Symmetric tensors. That's it. No other properties, right? So all we have to say is that this epsilon alpha beta is a symmetric tensor, and we're done. In general, for a spin s particle, the labels are just 2s alphas or alpha dots, whatever you like. Okay? And if you say that, automatically, if you convert back to these guys, you'll discover that it's transverse, for example. Okay? And that extends to all the higher spins as well. You don't have to take out the traces. Okay, so, and if you want very concretely to extract the different spin components, then for a massive momentum, you can always decompose it as a sum of 2 sets of spinor helicity variables with this normalization between them, and then concretely the helicity minus s polarization is just the product of all the lambdas. The minus s plus 1 is one fewer lambda and an eta, again all symmetrized, all the way up to all plus s's, all etas symmetrized. But in practice, of course, we only do this at the very end if you care. Really, the amplitudes are just invariantly these tensors. All right, so those are the labels. For the massless particles, they're helicities, lambdas, and lambda tildes. For the massive particles, they're spin s tensors. Now we can go and write down all the possible 3-particle amplitudes. And just for the sake of time, let me just give you a tour of some of them. So for instance, if you have two massless and one massive, then it's completely trivial. Again, there's only one structure once you specify the helicities of these guys. Okay? It's just some number of lambda 1s and lambda 2s, and all the weights are made up by, everything is fixed by the little group weights. Something that's totally trivial in this formalism, and things, for example, like Yang's theorem, that a massive spin 1 particle can't decay to 2 massless spin 1 particles is completely trivial. You just can't write it down. For the plus minus vertex, you can't write it down. For the minus minus vertex, it would violate both symmetry. So, okay. And also the polarization sums are utterly trivial because, again, you're not taking out a trace list. There's no trace conditions. You're just matching up indices with one side and the other. And what you get in the end is some beautiful combinatorial expressions like that, by the way, are very similar to some of the expressions Simone was showing you in the previous talk. But they're really this nice underlying combinatorics behind it. They're extremely simple objects. Okay, so that's not just true. These reproduce the Lejeune polynomials in the cases where these are scalars on the outside, but they generalize to all the spinning cases trivially. Okay, now, 2 massive and 1 massless. This is a little bit more interesting. The story is because, you see, I have to just make things that have alpha indices, and there's only one way of doing it. Well, I have the lambda for this leg, which I can call u, and I can take P1 or P2 on lambda tilde. That also gives me an alpha index. These are equal and opposite to each other, so I have two two-dimensional vectors, u and v, and I can look at the inner product between them, and that's m1 squared minus m2 squared. So there's 2 naturally different cases. If the 2 masses are different, then these 2 guys are a basis, and this is the most general 3-point vertex you can possibly have. Again, you just write them down, and you write down some number of u's and some number of v's, and you make all the little group weights work out right. In this case, it's labeled by a single integer, which you can think of as how many u's you put on this leg, for example. The case where the 2 masses are equal is much more interesting because in that case, these guys are not a basis. V is parallel to u. So I only have one 2-dimensional vector, lambda, but I have this constant of proportionality between the 2 of them, which is also an invariant of the problem. And so once again, all I can have, if I have this general situation, is some number of powers of x, some number of epsilon tensors between alpha and beta, and some number of products of these u's. Okay? So once again, there's a structure that's just labeled by one thing. So for example, here are some familiar things. Here's minimal coupling. Okay, so let's say you have a scalar. Standard, in the case of a scalar, there's only one thing you could possibly have. It's just m times x. But if you have a spin-a-half particle already, you can have 2 structures, m times x epsilon alpha beta, or lambda alpha lambda beta. And there are in principle 2 different coefficients there that are telling you the charge on the magnetic moment. Okay? But once again, minimal coupling, what it is physically, is nailed by the requirement that if we go to the high energy limit, the only couplings we have are the lowest dimension couplings that there are there, involving helicity plus h minus h and the other guy. And that turns out to trivially nail this structure to just be epsilons. If it's gravity, you multiply by another factor of m over m Planck x. And in this case, well, if I flip the dotted to the undotted indices, it would again just be epsilons, but if I can flip them back using the momenta, and you get this simple 2-dimensional tensor in town. Okay? So minimal coupling is also nailed, but that's just one set of possibilities. We can have many others. Okay, finally, the case of all 3 massive is similarly easy, but I won't talk about it. So I just want to say that the challenge is concrete. If you're given a spectrum of massive and massless particles, we have this set of couplings, and we know what they all are. We know what all the allowed tensor structures are. And now we want to find 4 particle amplitudes for all the possible different sets, which factorize correctly. And we know exactly what factorization means because we know explicitly what all the polynomials are that have to make an appearance. Okay? So I just went through that little technical exercise just to show you that it's a very concrete problem. You don't have to be, if you're scared of higher spin scattering amplitudes, you don't have to be. It's essentially as easy as massless ones. Okay? Now here's some very easy examples. But one fun thing about this formalism is that you can just sit down on a lazy afternoon and calculate all the 2-to-2 amplitudes in the standard model. Okay? Massive particles, anything you want. It's utterly trivial. So here's Compton scattering, for example. Okay? So here's the Compton scattering amplitude, and there's only one thing you can possibly write down upstairs. I don't have any time to explain it, but you just write down the answer and you check that it factorizes correctly. And actually, more exotic things are much easier to do. So here's a crazy example. You imagine there's some excited spin 3/2 partner of the top quark, and you want to see how it scatters off a photon and turns into a graviton. Okay, well, this is the answer, the most general answer it could possibly be. And everything is completely nailed by, in fact, there's only 2 couplings that appear there, and so you can just write down the answer ahead of time. No need to write down a Lagrangian, no Rarita-Schwinger formalism, nothing. Okay, you just write everything down. Notice, by the way, for fermions, there's no gamma matrices anywhere, obviously. Okay. All right, now, as a very first step into this general S-matrix program, we can show that massive higher spin particles must be extended objects. This is kind of a cool little exercise. We already knew that in the massless limit, they're simply inconsistent. You can't have them at all. We can't have massless higher spin particles at all if you allow them to couple to gravity, which they all have to do. Or if you have a charged particle, it can't have spin 3/2 or higher. That's also excluded. But obviously, you can have massive higher spin particles like this. We have, excitations of the hydrogen atom or nuclei. There's zillions of actual bound state objects that have high spin. So how does it work? How are these things consistent with each other? Well, the 3-particle amplitude, there's a piece which is minimal coupling, and then we can have all kinds of other structures. If you have a spin s particle, there's 2s plus 1 structures you can have. Minimal coupling is one of them. There's 2s others. And these 2s others set the size of the particle, as usual. They're dipole moments, magnetic moments, quadrupole moments, higher moments. Okay? Now, if a particle looks point-like, that means there's an approximation where you can forget about all those guys and then find consistent scattering of the particles that you have with everything else. So we can ask, for the massive particle, is it possible to have a consistent 4-point amplitude with only minimal coupling? And there's a 2-line argument that if there's a blackboard here I was planning on showing you, that the answer is no. You can prove that it's impossible. Okay, so you cannot consistently factorize a massive particle with minimal coupling. That means that you must have these higher order couplings, and their size is minimally got to be of order of the mass of the particle. Okay? So in that sense, massive higher spin particles must be extended objects. Now, notice that higher spin weakly coupled bound states like the hydrogen atom, the size is much larger than 1 over the mass by perturbative factor. Okay? Higher spins from strings are the limit where they saturate. Their size is of order 1 over m, and that's, of course, the only thing that we're forced into from this argument. All right, so I'm really out of time. Can I have 5 minutes? All right, great, because at least I want to show you something about strings, since I was talking about strings. So let's talk about the magic of string positivity for massless scattering and just a few trial deformations. If you start... So now we're going to ask, how does string theory satisfy these rules just for the lightest particle scattering? We start with Veneziano, where we just have tachyons. And so if we look at the residue as a function of t in the S channel, there's the tachyon pole at s equals -1. There's a pole at s equals 0, s equals 1, and so on. The pole at s equals n is just a simple Pochhammer symbol. And so if we look, the interesting thing happens with the residue at s equals 1. Here's what it is. It's just t plus 2, t plus 3. I can convert that to cosine theta, and I discovered that it's 25/4 times cos squared theta minus a 25th, that I can indeed decompose into Gegenbauer polynomials. There's that piece, which is spin 2, which, remember, depended on dimensionality, so that has a positive coefficient. That's OK. But there's a piece here, which is a spin 0, whose coefficient is 1 over d minus 1 over 25. And that's how you discover it is indeed non-trivial that string theory is unitary, and you discover the number of spatial dimensions has got to be less than or equal to 25. Okay, so you can't do it. This is an exercise in Polchinski's book, by the way. Okay? There's the analogous thing for the open superstring. Once we factor out this, the helicity pieces, it's very similar. Here's what the residues are again. Again, the first interesting thing comes when the residue is quadratic. And when I look at the residue at s equals 3, it's 9/4 cos squared theta minus a ninth, which decomposes in the same way. And you see that it's OK for d is less than or equal to 9. But already you see that it's non-trivial that this works at all. It puts a restriction on the dimensionality of space. And here is maybe the most, here is a thing that I want you to remember more than anything in this talk, because of how incredibly simple it is, okay? This is a polynomial. Okay? This is the residue that you get at the nth level in the open superstring, let's say. It's an utterly trivial polynomial. You could explain this to a kid in grade 7 or grade 8 who likes trigonometry. Okay? It's cos theta minus n minus 2 over n minus 4 over n. It just ladders all the way up to cos theta plus n minus 2 over n. Okay? So it's a polynomial with evenly spaced roots, almost between minus 1 and 1, but not quite. Just shifted a tiny bit away from minus 1 and 1. The statement that string theory satisfies unitarity is that you can expand this in Gegenbauer polynomials with positive coefficients. Heck, let's just go to 2 spatial dimensions where Gegenbauer polynomials are just the Fourier expansion. Okay? So this says that this stupid polynomial can be expanded as a sum over k, ck cos k theta with ck positive. The only known proof of this incredibly simple statement is the proof of the no-ghost theorem in string theory. Okay? Extremely, pretty long distance away from such an incredibly simple statement. I strongly believe there must be another proof of this statement. And if I had more time for this talk, I would give you a lot of circumstantial evidence that there has to be different proofs of this statement, because there are other things that are true which are related to this fact that is not at all obvious how the no-ghost theorem would know about. Okay? In any case, why is it hard to prove it? It's hard because these CKs become exponentially small while staying positive. And a quick way of seeing that is if you completed this polynomial by adding a last factor, which would be cos theta minus 1, just taking that last root, which is incredibly close to 1, and just making it 1, then the statement would be false. It would be false because if the cos theta minus 1 factor, if I put cos theta equals 1, on the left-hand side we'd get 0, on the right-hand side we have something manifestly positive. Okay. And there's a few useful facts about positive functions, which in playing with these things come in handy. One is the optical theorem, essentially, that when the x goes to 1, if you have a function that's a positive sum over Gegenbauer's, it's positive itself. If 2 positive functions exist, there's sum and the product is positive. If the function is positive in d dimensions, it's also positive in fewer than d dimensions. All those things are obvious. The most interesting one, which I don't have a conceptual understanding for, even though the technical understanding is trivial, is that if you rescale a positive function, it becomes more positive, in the sense that f of tx minus f of x is positive for any t bigger than 1. And that has many, many interesting consequences, but one of them is that f of x doesn't have any real roots for x bigger than 1. And the final thing I'll say quickly is that this open string positivity is primary. Starting from the fact that the open string polynomial is positive, all the other facts follow. For example, the bosonic string residue is one of these t bigger than 1 rescalings of the open string residue. The gravitational residue is the square of the open string residue. So by the fact that 2 positive functions are positive, that shows that it's positive. Interestingly, the gravity residue is quite a bit positive. It's more positive than it needs to be. If you ask for its local critical dimension, it's 23, okay, rather than 9. So it's not close to saturating it. Okay? But it's because it's the open string which is saturating it. And related to that, this correction term to the amplitude that I told you about in the heterotic string is not a positive function by itself. And that's why you can't make its size too large relative to the type 2 piece which is sitting there without running afoul of positivity. But the fact that the gravity piece is more positive than it needs to be allows these other deformations to exist. There are some totally, now we can ask about deformations. Can we have other amplitudes? There's a totally trivial one that you can have where you sum over string amplitudes with different string scales. There's nothing wrong with that. There is a strange deformation of the Veneziano amplitude that was written down by Kuhn in the late 60s, maybe very early 70s, which is a straightforward deformation of the Veneziano amplitude where the spectrum isn't linear but is replaced by this interesting, by that interesting spectrum itself, which, as you see, sigma is some number smaller than 1, and so it has an accumulation point. As n goes to infinity, mn squared hits a finite, mn squared is a finite. So there's an essential singularity at finite s and t. There's not obvious there's anything wrong with that. That's also similar for the spectrum of the hydrogen atom. But in any case, that's not allowed in the rules that we're talking about. So we can ask if there's any non-trivial deformations that don't have any essential singularities. And here we have found some interesting ones. We have found some interesting ones in some cases, basically borrowing the, let me just go to the, let me just summarize what we found, and I can tell anyone who's interested in more detail. We found that the positivity of the string amplitudes is indeed pure magic, but with just massless scattering, we have found some deformations that inherit this magic. So if we didn't know about the string amplitude, there's no way we could write these things down, but since we know them, there are interesting deformations. There are even interesting candidates for what look like pion scattering amplitudes that look like hard scattering, not exponentially soft scattering at very high scales. There are deformations of Yang-Mills amplitudes. There is exponentially soft deformations of gravity amplitudes. So all of this is an indication that we have to look at consistency of amplitudes involving the massive higher spin particles, not just the massless ones. And no time to talk about that. Let me just say that for the next steps, there are some totally obvious things to extend figuring out what the rules are for the 4-particle S matrix to general D and to supersymmetry, to try to prove the positivity of this polynomial in a new way that also explains some of the things that we found, some of the deformations that we found that remarkably don't work, involve things that can be interpreted by taking this polynomial and multiplying it by a factor which has a root that's even closer to 1, by something that scales like 1 over n squared rather than 1 over n. So here's an example. This polynomial is positive, and that follows indirectly from the no-ghost theorem. But if you multiply by this thing, it's no longer positive for any c. Why is that? It's hard to see how that seems to be a true mathematical fact. It's very hard to see how it follows from anything we know about the no-ghost theorem. So it really seems to me that there's an interesting world of mathematical objects involving these positive functions that we should try to understand better. Okay? And indeed, we've started looking at amplitudes involving massive higher spin particles. We've computed the amplitudes in the bosonic string with 3 tachyons and massive spin 2, 3, 4 higher particles on the leading Reggie trajectory. And the only thing I'll say about it is that we see the same kind of polynomials making an appearance, but curiously, we find that these polynomials' positivity does not follow from the positivity of the lowest lying states, and there seems to be additional, even more constraints coming from the study of the higher massive spins, exactly as you would naively expect, exactly as there needs to be. All right, so let me just end by saying that I think for this subject, we need more data. For the greatest S-matrix theory of all time, at least by my, it seems to me, our understanding of string amplitudes is very primitive. For example, even forgetting about the amplitudes, we don't know explicitly the bosonic string spectrum covariantly. If you want to know at the 123rd level what exactly are the higher spin states, we have no idea. Of course, we know in principle how to do it, but we don't know explicitly how to do it. There was papers by Goldstone and Thorne from the 80s and by Hanani around 10 years ago that just counted them. Counted how many of them there are. Even then, the formulas are not manifestly positive. You can put it in Mathematica and get an answer, but they're not manifestly positive. So we don't even know what the spectrum is. Never mind what these couplings are. For example, if we knew the spectrum, we could then ask what is the 2 tachyons, 1 massive higher spin coupling. If we knew this formula, I would at least be able to give an expression for expanding that polynomial in the sum of Gegenbauers. We don't know the spectrum, we don't know these couplings, so I don't know how to do it. And I think, to me, the most interesting conceptual question of all is that we started the talk by saying how beautiful it was that the 3-particle amplitudes for massless particles are fixed by Poincare, and then a whole rest of the structure can develop away from that. But in string theory, of course, from the usual way of thinking about string theory, we know how to compute these couplings in principle, not in practice, but in principle. But it would be wonderful if there was some question to which these 3-particle amplitudes were the answer. Okay? What principle fixes these 3-point amps? And if we know the answer to that question, perhaps we can start doing things that we did analogs for, again, in Yang-Mills theory. When we had maximal supersymmetry, we had many, many different helicities. And it was a good idea to combine them into on-shell states that made the action of the supersymmetry manifest. If there is some kind of symmetry, some avatar of the higher spin symmetry that fixes the structures of these 3-particle amplitudes, perhaps there's some avatar of these etas that would be a covariant on-shell string representation that would allow us to trivialize these 3-particle amplitudes. And then we wouldn't be doing what David's complaining about, which is talking stupidly about one of these massive higher spins one at a time. But perhaps there would be some more stringy, but more on-shell, less gauge redundant stringy way of doing it. All right, thank you very much.